Good evening, everybody. Thank you, Lori, for the very generous and kind introduction. Lots of familiar faces here tonight. It's great to see everybody, especially post-pandemic when we haven't been in person much. I have delivered boots on the ground previously, but never in person, so this is a first for me. My talk tonight is called Scaling Up Passive House, Net Zero Buildings, and How Do We Get There Faster? We're going to go through some of these things. Lori introduced our company briefly, Passive Design Solutions. I've been working exclusively on passive house projects since 2009. So going on, 14 years. And I want to see things move faster. As Lori mentioned, we do a lot of custom design and construction support. One of the things that we've done to really try to move things in the market is develop a series of custom passive house stock plans. And Lori mentioned working North American wide, and it's really been the stock plans that we've worked in a lot of jurisdictions, from Inuvik to Colorado to Newfoundland and all parts in between. So it's been a great tool to get passive house more into the mainstream. And currently we're working on about 100 projects a year, and it's still not enough. We need to move faster. And why? This is a great graphic. I like it. You probably can't see some of the labels, but the image on the bottom left is 1979, number of days above 100 degrees is shown in this graph. And the best case scenario of emissions going forward is the middle, and the worst case of emissions is the far right. So we have a big problem. And I know I'm preaching to the choir. We have a problem where we're using a lot. The majority of our energy is generated through fossil fuels, and this continues to grow. And that first chart was in the year 2000. This chart is 2020, and you can see our growth in emissions is actually growing. We're emitting more and more since 2000. So we're not turning the train around yet, and the problem continues to get worse. This CBC Nature of Things Apocalypse Plan B, Harnessing the Sun, is where I grabbed this screenshot from. Great little documentary if you're interested. This image is also from that TV show, and it shows in 1 year the emissions in coal equivalent. That's Central Park, and the pile of coal is 4 kilometers high. That's in 1 year. Well, we know we need this transition, and 50% of that transition needs to come from energy efficiency. Everybody sort of agrees that we can make great grounds through efficiency, and then what we're going to try to do is reduce our fossil fuels and start generating energy with greener fuels. We all know that Canadian building stock is a big user of energy. We live in a cold climate, and this is from Enercan. It shows that about more than around 83% of our total energy goes to heat, cooling, and hot water in our existing building stock. So there's our opportunity. We also have a growing problem with storms. We have a long-term probability of survivability we're just having more intense and frequent storms. I don't have to remind anybody in this room about Fiona and the impact it had. And we also have volatile politics and energy security worldwide, which is also a pressure on energy use. I'm actually kind of concerned of where we are in the world, that war is going to make everybody forget about climate change, and that'll be the focus for the next 5 years, and those are 5 years we can't afford to lose. We have our short-term emergencies. My mom was without power in Fiona for 11 days. She does live in a passive house, so she was okay. But we have safety for our occupants and also for our buildings related to long-term power outages. And firing up generators, small two-stroke engine generators everywhere in every neighborhood is not the solution. So we go right to site net zero building, right? And for those of you who may not know, net zero, as I define it, is producing as much energy on site annually. So, and we are also using, and the most practical way to do that is net metering, using the power utility so that you're feeding that energy into the grid when you're overproducing, and then you're using it in the wintertime when you're underproducing. So net zero is, the approach to net zero, I think, is bigger than that, and we need to take care of a few things in our approach to building sustainably. First, to reduce the embodied energy in our materials. Okay, so we can build a really super efficient house, but if we created a whole bunch of emissions in making those materials, we're no further ahead from in the climate crisis. We also want to reduce the operational energy. That is both for energy security, but also reducing overall emissions. We want to reduce peak power loads, and we want to design durable buildings. If you have to tear them down because they're full of mold in 15 years, again, we're not serving the planet with our use of materials. We need to make beautiful architecture. We know that ugly buildings don't last long. They get torn down. So again, we're creating more use of materials. We want to design for simple maintenance, and we want to keep an eye on the recycling of those materials at their end of life. Those are all this is my approach to sustainable building. So we have our list. We have an easy solution. Why don't we just build code-built buildings and put lots of solar panels on them? Why not? Anybody? Yep. Not enough space on the roof. That's number one. So I don't think our neighbors would appreciate these overhangs. And on multifamily, that's next to impossible, right? We just don't have the roof space. Another reason, we can't just build co-built buildings.
Embodied carbon.
Okay.
Use way more material than you need to.
Yeah. Yeah, there is a lot of embodied carbon in solar panels. So, yep.
Okay, so the grid can't necessarily handle it?
Yeah, we're going to talk about peak loads, but I'm going to skip to one more before. I got 3 reasons why not to do this. What's the next one?
Operational energy.
Yeah, keep going. Lori, come on, you know this.
Embodied carbon and solar panels?
Yeah, there is a lot of embodied carbon in solar panels. Yeah, for me it comes to comfort and durability and resilience. Okay, so if we build co-built buildings and the power grid goes down for 11 days in the winter, those buildings are going to freeze and the occupants are going to be affected by that. If we build passive house level buildings first, and actually just let me back up for a second. The second point about building co-built is you need a big furnace. Okay, and we're going to look where that puts us, look where that takes us in a minute. So passive house uses these factors to measure comfort, and really you can forget about all the numbers around those factors. What it really means is you need a tiny furnace. Okay, if you've designed it properly, you should have a very small heat load. You should be able to heat your house on the coldest night of the year with the equivalent of 1 or 2 hair dryers. That's what the size of a heater we're talking about. Okay, so we need a tiny furnace for comfort. The other reason we need a tiny furnace is how the grid works. Okay, and this is called the duck curve. And I don't even know whose grid this is, but it represents a sample of what happens on pretty much every grid. So we have this, for those of you that can't read it, we're going from 12 in the morning, 12 a.m. to 9 p.m. And you can see that the power is kind of consistent, and then it drops drastically. And you can see it's dropping further and further over the years. That's because of solar. Solar is making energy and feeding it into the grid. So the demand on the grid is less during the 9 a.m. to 6 p.m. when the solar panels are generating energy. But then when we get past 4 o'clock, we see that there's this massive ramp up of power. Everybody comes home, they start cooking, they start doing their laundry, they turn up their heat, and this ramp up is a problem. It's a big problem in Nova Scotia because the way we meet those peak loads is with coal-fired power plants. There's 9 coal-fired power plants in Nova Scotia that are mainly online to meet peak power requirements. And I heard someone from Department of Environment say they cost about $450,000 a year just to keep open, just to keep operational. And we're using them just to meet peak power. So then we're all going to get electric cars, right? We're going to take them home and plug them in at 6 o'clock. And we're going to increase peak power again. So how can we use our buildings to contribute? This is some monitoring data I pulled from the first passive house we did, and we got some monitoring data. I used the same timeline from midnight to 9 a.m. This project is on time of use, so the heat comes on in the low times overnight. So we can see that the energy used in the nighttime is the majority of the energy that the house needs, because it's the heating and it's the hot water. The rest of the utilization during the day, if we're using good daylighting design, if we're using efficient appliances, we can really minimize those loads and the time of those loads. If you compare that graph to this duck curve, it's kind of the complete opposite. And we could program our, if we need to use more energy in the middle of the day, we can easily program the houses to do that. We can put things on timers so that heat runs at that point in time. Okay, so that leads us to the idea is that we need to conserve energy first. Reduce, reuse, recycle. Again, same principle. We need to conserve before we start putting renewables on our projects. So PH, passive house, for those of you that are new to this idea, takes the levels of efficiency to a fairly, it's kind of on steroids. It's very high levels of conservation. And Efficiency Nova Scotia folks say conservation is the cheapest fuel. And that is true. We want to conserve energy first. It's cheaper than just piling panels on a roof space we don't have with a code-built building. The real prize is it yields comfort and it yields durability and resilience during storms, which we're going to get more of. So I know I'm not going to be in the right spot, but I'm going to stand over here, this far here. So I have two images on here. The first is a code-built house. The left side is the inputs into the house. And you can see the big red bar in the middle is mechanical heating. Okay, the little red circle on the bottom is internal heat gains. And then I said both houses could get the same amount of energy for the sun, just to be fair. Okay? And then that's matched with transmission losses. So we have envelope losses, windows and doors, air leakage, and ventilation and mechanical energy. And if we make the building a passive house, you can see that we've reduced all of those losses on the right side, and now we can use a fraction of the mechanical heat to make the house comfortable. This is a annual monitoring results from the Hawkins House, the first certified passive house in Canada that we did. You can see, for those who can't read it, the light green bars are lights and appliances and plug loads. Everything else is mechanical. So in a passive house, if you remember that chart we had, we are now 60% of our energy is lights, appliances, and plug loads. And we're down to 40% of the loads being heating, cooling, and hot water. Compare that to the average Canadian house, where we've got that 80% is heating and cooling. And really what I should have done is made that little pie chart about 70% smaller than this pie chart, because the overall energy is that much less. True North is a project I'm really excited about. It's an affordable housing project with mixed rents. It's 4 sites donated by HRM for 44 units, and they're going full net zero. And the AHANS, the Affordable Housing Association of Nova Scotia, has really identified that they can't make their model work without net zero. They can't afford to pay energy bills, and they don't feel they can charge the tenants in these affordable housing projects for the energy. So we are going full net zero. This is from the report on the energy modeling of this project. 4 buildings. The blue is the code-built base case, reference case. The orange is the energy used annually with, without any solar on the roof. Okay, so we're reducing first. We're reducing by over 70% on the slightly different building types. And then when we add our solar panels, we're reducing that annual energy use by 100%, getting down to 0. This is how it breaks out. The code reference case is the big red bar. Hot water is next. And then everything else is below that. Energy from fans, HRVs, appliances is yellow, lighting, and miscellaneous loads. In the proposed case, or the way it's actually being built, you can see that red is drastically reduced, and we've also drastically cut hot water. So the amount we have to generate in the green bar is quite small. And people say, oh, there's no way you can get to net zero and have it be cost effective. Yes, of course it costs more to get to net zero, but if you're going to go to net zero, building envelope upgrades are more cost effective than solar panels to a certain extent, okay? So these are the numbers. So if the upgrades in each of these buildings are shown in green, the upgrade costs, and if we replaced, if we didn't do those things and had to replace that energy with solar panels, the cost of those solar panels is in blue. So it would cost us more to generate that energy than it does to save it by a substantial margin in all 4 buildings. My 3 plugs. 50% of your energy efficiency comes from good design. If we build buildings with jigs and jogs and in plan and section, it will be very difficult to make an efficient building. You can still do it by spraying the money gun at it, but it's a lot easier by good design, okay? Small is better. It's better for the environment if we build the smallest possible spaces that can meet the program design. I was out at some clients' house today. They're here tonight. And we were talking about some of the other houses that are being built in their neighborhood, 37,000 square feet, home on the ocean, right? So maybe a little hard on the planet for 2 people.
Careful, that client might be in the room.
Might be in the room. Yeah, I doubt it, but I'm willing to talk to them if they are. Energy modeling. We must use the it's not a passive house if it's not energy modeled. You must use the energy model to do sensitivity analysis to find the most cost-effective path to net zero. And you know, whether you're hitting targets or not, it depends on climate, orientation, shading, building shape, number of factors. So every project needs an energy model, and use that energy model to figure out that balance of where you stop upgrading the building envelope and where you start adding renewable technology. So some of the things we've done on these multifamily buildings to control cost, larger buildings can use thinner assemblies because they have less surface area to square footage, so they're just generally more efficient. We are balancing the levels of insulation with the cost of solar panels. Hot water heat pumps are a no-brainer. The second largest energy use in any building is hot water, and we must reduce those loads as well as using efficient design. We like to use a locally supported passive house window manufacturer. For many years, I imported windows from Winnipeg, and I've replaced many of them myself because there's no service here. And then in these particular projects, heat pumps were cut from the budget to minimize cooling loads. So in affordable housing, we really don't know how to solve the problem of the tenants opening up the windows and cranking the air conditioning. And the affordable housing not-for-profits are very nervous about their cash flow and making their projects financially viable. So we designed these buildings for their cooling loads. We eliminated as much cooling as we could, and then we eliminated cooling systems. The Sunflower House at Halifax is a net zero project. In Timberley, it is 25 units and a community center, and it supports women and children at risk, many who are coming from homelessness. And it was a really successful project for us. We had a no ego, highly collaborative team. And we had really smart structural, electrical, and mechanical engineers that were willing to do things differently and not just do the same old, take the same details that they're always used to. We used the experience we had in Passive House to kind of limit the design options and be smart on the building shape and orientation and so forth right off the bat. And we used the energy model for the sensitivity testing to figure out how much upgrading to do. We used panelization during construction. It was actually a requirement of the Rapid Housing Initiative. This project was funded by the Rapid Housing Initiative. And wherever we could, we used locally available materials and equipment. This is the finished project. I think it's a pretty neat little project for a deeply affordable project. The rents in here are between $300 and $500 a year, and they will only increase by cost of living for at least 20 years.
Was that a year or a month?
Sorry, what did I say? 300 a month, sorry. Thanks, Matt. So what I want to do tonight is leave you with the thought that we need to do more and we need to do it faster. And everybody that's in this room has an interest in making this move towards a fight in the climate crisis, and we are running out of time. The data shows that. So here's kind of my ideas of what we could all do in our own work that will help us move faster to scaling Passive House and net zero up as quickly as we can. So again, locally available materials with local service. Consider the embodied carbon in your materials and the global warming potential of your materials, so the off-gassing in the manufacturing of those materials. Use cost-effective passive house strategies before renewables, get that balance. Reduce your overall site energy, so we have sustainability in many ways. Reduce the peak loads on the grid, especially at peak times. Make all buildings electric. And I'm not so sure that the final solution is site net zero. I think that our final solution is probably all electric buildings with a green grid. Nova Scotia Power, when Muskrat Falls comes online, will be 60% non-carbon electricity. And I'm not sure that every building is going to have the orientation, the access to the sun, or other factors that are going to affect being able to be site net zero. But by building very low energy buildings that are all electric buildings, we are prepared for the future of having a very green grid to support that.